This is a lesson about antiderivatives or integrals. This is an exciting day. We get to find the second thing we do in calculus. In calculus, there are two things you do. You take derivatives and you take antiderivatives, which are the integrals. That's basically it. Two things for calculus. So in example 1, if a function is y equals x cubed, then we can find the slope at any point with the derivative. Okay, well, what is the derivative of x cubed? The derivative would be 3x squared. I brought the power down and then dropped the power by 1. But now we know how to take derivatives. What if we want to go in the other direction? Okay. So what if we want to find the original function that had slope of 3x squared? What would we do? So if we were to say, if we know that the derivative of a function is 3x squared, well then what would f of x be? What was the original function that gave us the derivative of 3x squared? Well, in this case we could say that it must have been x cubed, because in our last example we said if we start with x cubed and we take the derivative, we get 3x squared. So now we're saying if we want to go in the opposite direction, if we want to say take the antiderivative, if the derivative is 3x squared, the antiderivative or the original function would be x cubed. So let's practice, and at this point we're basically guessing and checking. So let's say if f prime of x equals 2x, then what was f of x? So what would you have to start with to get a derivative of 2x? So let's kind of guess and check. So I think it might be x squared. If I start with x squared, let's take the derivative again to double check. The derivative would be 2x. That's what it was supposed to be. So my antiderivative of 2x is x squared. Let's see. If the derivative is 1 over x, what was my original function, f of x? So how do you get 1 over x as the derivative? That would happen if you started with an original function of natural log of x, because the derivative of natural log of x is 1 over x. So it's kind of, again, working backwards, just trying to guess and check. Okay, so if f prime, if the derivative is x to the 5th, what was my original function? Now I know when I take the derivative that I drop my power by 1. So if I'm taking the antiderivative, I probably want to go in the opposite way and raise my power by 1. So I think I might start with x to the 6th. But now here's where the guessing and checking really comes in. If I was to take the derivative of that, I would get 6x to the power of 5. That's not quite right. I'm supposed to have x to the 5th. Okay, so how could we combat that? I have this extra 6 I don't want. So what if I come back to my original function and instead I do 1/6 x to the power of 6. So now let's double check. So taking the derivative, 1/6 would still be there. I bring down the power of 6, drop the power by 1. Those 6's cancel and I'm left with x to the 5th. So when we do these antiderivatives, it's nice. You can always take the derivative to kind of double check your work because you know how to take derivatives well by now. So my final answer is that f of x, or my original function before they took the derivative, must have been 1/6 x to the 6th. So now we have a technical point. This is actually going to be very important, and we'll use it a lot. But let's look at all of these different functions and find the derivative of each one. So the derivative of x squared is 2x. The derivative of x squared plus 5 would be 2x plus, what's the derivative of 5? Just 0, right? So just 2x. My next one, x squared, that derivative is 2x. The derivative of negative 3.1 is 0. And derivative of x squared is 2x, and the derivative of 100 pi, pi is just a number, so it's just like having a 3.14 there. And the derivative of any constant here is just going to be 0. So really, I don't even need these plus and minus zeros. So the derivative of all of these functions was 2x. So now, if I was going to come through and say, okay, my derivative is 2x, what was the function I started with? Well, can you tell me if I started with x squared or x squared minus 3.1? I don't actually know which of these functions I started with. In fact, I could have started with an infinite number of functions, and all the derivatives would have been 2x. Specifically, f of x could have been x squared plus c, where c is any constant. Because when you take the derivative of any constant, you just get 0. And so I don't know which function I started with, so I'm going to tack on this plus c to all of my answers, just in case, to kind of be that technical constant to say, okay, I acknowledge that they might have started with a plus 5 or a plus 7, plus 10, I really don't know, so I'll just put a plus c on there to be accurate. Now we also have kind of a fancy symbol that we'll use. So how would we say that we want to find the antiderivative of, say, 2x with respect to x? What we'll do, this is called the integral sign. It's kind of like a really big, skinny s. Well, right, we want to take the antiderivative of 2x. But I need to tell someone what my variable is that I'm interested in. So I'll put this dx. And in fact, your symbol, this integral and the dx, kind of go together. You will never see one without the other. And it's important that you actually write these down. As you're doing your work, make sure you write your integral signs and make sure you tack on the dx. So this together is kind of like one big symbol. They go together. And then inside, you put what you actually want to integrate. So in this case, I want to integrate 2x, and that goes in the inside there. So we don't really like guessing and checking, so we can learn the actual power rule. The power rule tells me if I want to take the integral or the antiderivative of x to some power, I raise my power by 1 and then divide by my new power, plus c. Again, every time we take the derivative, we will tack on plus c, because they could have started with any constant, and then when you take the derivative, the constant goes away. So we don't know what constant they started with. Okay, so again, I don't remember this formula. I remember the kind of statement, I raise the power by 1 and divide by the new power. So in example 7, we want to find the integral, or the antiderivative of x to the power of 5. So x to the power of 5, I need to raise the power by 1 and then divide by the new power. So x to the 6 over 6 plus c. Or if you prefer, I often write it as 1 over 6 x to the power of 6 plus c. Doesn't matter. Okay. Example 8, we want to find the integral of 1 over x dx. 1 over square root of x. I would rewrite this first as x to the power of negative 1/2. 1/2 for the square root, negative because it's on the bottom. So I rewrote it. Now I can take the integral. So I raise the power by 1. Negative 1/2 plus 1 is 1/2. So it's going to be x to the 1/2 over and divide by your new power. And I can simplify this. Dividing by 1/2 is the same thing as timesing by 2, and so it's 2 square roots of x plus c. Okay, don't forget that plus c. Take the antiderivative of 5 dx. So again, I'm going to rewrite that. That's the same thing as 5 times x to the power of 0, right? Because anything to the power of 0 is 1. So 5 times 1 would still be 5. So you don't see it there, but we're going to say that it's really times x to the power of 0 dx. So when I take the antiderivative, the 5 gets to stay there, and we'll talk about that in a minute, why that is. Okay. And then x to the power of 0, 0 plus 1 is 1. So x to the 1 divided by 1, or in other words, just 5x plus c. Don't forget that, plus c. If you're not sure if you believe me, go ahead and take the derivative of this. The derivative of 5x is 5. Derivative of c is just 0. So I'd be back at 5, which is where we started with here. Okay, so again, this is a handy trick there. If you need to take the integral of just the constant, pretend that it's times x to the 0, or rewrite it as x to the 0. Now there's a few more rules, a few interesting things. So that power rule that we did up above did not work for the special case of r equals -1. And here's why. Because they said the integral of x to the r dx is equal to 1 over r plus 1 times x to the r plus 1 plus c. What happens if we try that for r equals -1? The integral of x to the -1 dx. So if we were trying the rule, it would be 1 over -1 plus 1 times x to the -1 plus 1 plus c. Or in other words, this would be 1 over 0 times x to the 0. Okay. there's a few things that are wrong here, right? We can't divide by 0, and timesing it by x to the 0 would just give me a 1, which wouldn't be very interesting, but mostly we have this dividing by 0, and that's bad, so we can't do that, so that doesn't work. This is why the power rule does not work for the special case of r equals -1. But we do have a rule that does work, the natural log rule. So what's the integral of 1 over x? Up above, in example I think 4, we looked at this and we said, oh, how do we get the derivative of, or how do we take a derivative and get to 1 over x? It must be when we start with natural log of x. Now there's a specific thing here. We need to put in this absolute value, and the reason why is that 1 over x is defined for all x's except for 0. Okay, because you can't divide by 0. And so we need to define our integral for all x's as well, and so we put the natural log of absolute value of x because natural logs can't have negative values. Okay. The exponential rule, if you have e to the kx, the integral is just going to be 1 over k e to the kx. Now there's some basic properties. The first one says if we want to integrate f of x plus g of x, we can do two separate integrals. Or in other words, you just take the integral of each term separately. So you look at one piece, do the integral, look at the next piece, do that integral. Okay, and also if you have a constant k multiplying your function, you can just bring it outside of the integral. So we bring it outside of the integral. You don't have to worry about that. It's just like what we did with constants or coefficients when we did derivatives. They just kind of stay there. We don't have to worry about them. So with all of those rules in mind, let's try this example. Okay, we want to take the integral of 3x to the 5th minus 2x plus 7e to the 6x. Okay. So I'm going to rewrite this. I could do the integral of 3x to the 5th. Now I'm going to split it up minus the integral of 2x. Plus the integral of 7e to the 6x. Dx, dx, dx. Remember, you will always attach that dx for every integral. And so this might make it look a little bit simpler, or maybe more complex, but it's telling us we can do the integral of each piece, one piece at a time. Okay. Now, even these numbers we can bring out. So it's the 3 times the integral of x to the 5th dx minus, let's bring out the 2, integral of x dx, and I'm going to write this as x to the power of 1, we'll explain why in a second, plus 7, integral of e to the 6x dx. Now that we split everything up, we're down to the things that we know how to take the antiderivative or integral of. So the 3 just stays there. Okay, now x to the 5th, the rule says you take the power, raise the power by 1, divide by your new power. Minus 2. Now this x, I put the power of 1 on there because it is x to the power of 1. We just don't usually write that. So I'm going to raise the power by 1, so I'll be at 2, divide by my new power. Plus the 7. Now e to the 6x. Go back up above and look at your formula that we haven't actually tried yet. If you have a number there, that k, you bring it out, so it's going to be 1 over k e to the kx. So the integral of e to the kx equals 1 over k e to the kx. So in this case, k is 6, so 1 over 6 e to the 6x. Now at the very end, I put a plus c. I don't need to put a constant for each one because they all just kind of lump together. If I added some constant here and some constant here and some constant here, at the end I can add all my constants and I'm still just at a constant. So we just add one big plus c at the very end. We can simplify that a little bit. So x to the 6 over 2 minus x squared plus 7/6 e to the 6x plus c. Don't forget your plus c. Okay. Now you'll notice here I took a lot of steps of where I pull out my numbers, I separated it. After you practice, you probably won't write it out. You'll probably just do each piece as it's written in the original problem. But you realize that that means you only have to look at each piece one at a time. You just don't actually write it out all the way. So like for this example, I'm going to first rewrite this integral as it's the integral of, well, we'll keep that 1 over x plus 5 times x. I'm going to write it as x to the negative 7 dx. Now when I do this, I'm not going to write out every step. Okay, instead I'm going to say, okay, what's the integral of 1 over x? This one you just have to memorize. The integral of 1 over x is the natural log of the absolute value of x. Now let's do this 5x to the negative 7. That 5 just stays there. Okay, now x to the negative 7, we raise the power by 1. So negative 7 plus 1 is negative 6. Divide by your new power. And at the end, plus c. So in this case, we have the natural log of x minus 5/6. We'll move that x to the 6 back down to the denominator because I had a negative exponent, plus c. And again, at this point, because you should be better than taking derivatives than antiderivatives, you can always double check your answer by taking the derivative and you should be back to where you started. So the derivative of natural log of x would be 1 over x. Derivative of negative 5/6 x to the 6 would be negative 5/6 x times negative 6 x to the negative 7th. Okay, so that would work. Derivative of c is 0. Now, sometimes we're given a specific value of our function so that we can find c. So here's an example where if we want to find the antiderivative for x squared minus 2, the integral of x squared minus 2 dx would be equal to what? Let's see. Derivative of x squared, raise the power by 1 and divide by your new power, minus 2. Okay, now this 2, that's really like 2 times x to the power of 0. You just don't normally see in there x to the power of 0. So we'll raise the power by 1 from 0 to 1 and divide by our new power of 1 plus c. So in other words, x cubed over 3 minus 2x plus c. Okay, so over here, this is the graph of x cubed over 3 minus 2x plus c. And I've graphed it with several different values of c. You'll notice it looks the same. Okay, each graph looks the same. It's just shifted up or down by c. So what if we wanted to find the specific function f of x? So these are lots of possible functions. But in example 15, we want to find the specific one where f of 1 equals 4/3. So we already know, okay, so we said the derivative is x squared minus 2. So if we want to take the antiderivative, we said up above that it's going to be x cubed over 3 minus 2x plus c. So what we want to do is find c so that f of 1 equals 4/3. So to set this up, we'll say, okay, so 4/3 equals, and now we're going to plug 1 into my derivative. So 1 cubed over 3 minus 2 times 1 plus c. So we have 4/3 equals 1/3 minus 2 plus c. Or I can do 4/3 minus 1/3 plus 2 c equals 3. And so for my final answer, I can say, okay, my final f of x was x cubed over 3 minus 2x plus 3. So usually we'll just do a plus c at the end, but if they give us a value that was on the original function, we can go through and we can actually figure out what c is. Our textbook calls this solving a differential equation, okay, because we started with an equation that involved our derivative. That's why it's called a differential equation. So, almost done. There's a few applications for this. Okay. One is if you're talking about position and velocity for physics, if you're talking about rockets, things like that. So remember, if we take the derivative of a position or a height function, we get the velocity. So now if we take the antiderivative or the integral of the velocity, we'll get back to our height function. Okay, so you can see here our original function, we use the notation s of t for our height or position. Our first derivative, v of t for velocity, and our second derivative, a of t for acceleration. So as you take the derivative, you can go from height to velocity to acceleration. If you want to go the other way, if you want to go from acceleration to velocity or velocity to height, you take the integral. Okay, and you can see an example in your book with this. And then also, if we want to do a business example, we can do marginal profit, cost, revenue, etc. So we find the marginal profit by taking the derivative of profit. Okay, and our textbook, at least in this chapter, is going to use the symbol MP of x to signify marginal profit. And the marginal profit tells you how our profit changes as our number of units sold changes. Or in other words, remember, your derivative always tells you a rate of change, how you're changing. Okay, but now that was before when we did derivatives. Now, what if we start with the marginal profit? So we start with the derivative. You can then take the integral to find your original profit function. Or in other words, you can take the integral of the marginal profit and get back to profit.